A lithium battery is one of the more contemporary mobile power storage types being used today. I will point out that lithium batteries are significantly more expensive than lead acid, like 4 or 5 times more expensive. So as a drop-in replacement for a starter battery that is seldom run down to less than 80%, they are not a good investment. Not as a starter battery anyway. However, as a leisure or recreational battery, they are certainly a realistic consideration. Let me explain what the pros and cons are to lithium batteries, or, to use their full name, a lithium-ion battery. Yep, that's what their full name is, lithium-ion. That's Lithium-ion. I'm going to use a 12-volt 100 amp hour lithium-ion battery as an example for this tutorial, which is almost the same physical size as a lead-acid 12-volt 100 amp hour motor vehicle starter battery. Pro number 1. A lithium battery will give you a fairly even rate of power from when it is fully charged, that being its state of charge being 100%, or sometimes abbreviated to 100% SOC. SOC meaning state of charge. The battery will give you an even flow of electricity from full all the way down to 1% of its SOC, or its total power. Unlike a lead-acid battery that will depreciate in its power as it runs down, like you would see your lights dimming down before the battery eventually gives up. A lithium-ion battery doesn't do that. It will give you full power, full lights, until there is nothing left to give. Note, you should never discharge a lithium battery to 0% if it can be helped, as it is destructive to the battery's internal workings. Pro 2. This is often the deal maker. A lead-acid battery should not be discharged to less than 50% of its capacity, or you might deteriorate its internal workings. Therefore, a 12-volt 100 amp hour lead-acid battery only really works out to be a 50 amp hour lead-acid battery. You're only really getting half the advertised power capacity in a lead-acid battery. However, in a 12-volt 100 amp hour lithium-ion battery, you will get 98 to 99% of its advertised power capacity. So, this would make a 12-volt 100 amp hour lithium-ion battery pretty much the equivalent of two 12-volt 100 amp hour lead-acid batteries. So, you're getting double the power for roughly the same footprint or size of the lead-acid battery. Pro 3. A lithium battery can be run down and recharged many more times than a lead-acid battery. A lead-acid battery can be discharged and recharged somewhere in the region of 500 to 1500 times. However, a lithium-ion battery can be discharged and recharged somewhere in the region of 3000 to 4000 times. So clearly, if a lithium battery is looked after, it will significantly outlast a lead-acid battery many times over. Pro 4. Lithium batteries are usually quite a bit lighter in weight than lead-acid batteries, often 30 to 40% lighter. Pro 5. Lithium batteries can be used to fit into spaces that are not normally designed for the standard lead-acid battery type. As long as they are wired correctly, their smaller size and modular shape and design can allow them to be placed where space is at a premium. So, there we have 5 reasons why lithium batteries might be a little more desirable over lead-acid batteries. 1. An even rate of power over their entire discharge. 2. A full usable 99% of the battery's power capacity. 3. A significantly longer battery charge-discharge cycle life. 4. Lithium batteries weigh less. 5. They might be manipulated and arranged differently to fit varying layouts. Now the cons. Con number 1. Lithium batteries don't like the cold. Trying to charge a lithium battery when it's freezing or below freezing will potentially ruin the battery. It's okay to use power from a lithium battery when it's below freezing, but not okay to try and charge a lithium battery when it's freezing or below freezing. This problem can be helped by the assistance of a battery management system, or BMS. Some lithium battery manufacturers have introduced a heating blanket system that warms batteries up just before freezing. Now, con number 2. Lithium batteries can get overheated, and this needs to be monitored and checked. This problem is usually addressed with the assistance of a battery management system, or BMS. Con number 3. Lithium batteries need to be balanced, and the balance maintained. Balancing devices can be expensive for good quality units. They are known, generally, again, as lithium-ion battery management systems, or BMSs. More on BMSs later. Con number 4. Lithium batteries can be overcharged. This problem, again, can be helped with the assistance of a battery management system or BMS. Con number 5. Lithium batteries should never be completely discharged down to 0 volts. This problem can be helped by the assistance, again, of a battery management system or BMS. On the whole, lithium or lithium-ion batteries need a bit more care and attention than their equivalent in the lead-acid battery world. If they get that extra care and attention, they will significantly outlast lead-acid batteries. That needed care and attention that lithium batteries require has been built into some lithium batteries, or may be purchased as an automated modular device, a BMS, a battery management system. As of this time in 2022, there are generally 3 different lithium battery shapes. There is the large block shape, usually containing 4 or more lithium battery cells that have been wired together, designed to drop in where a prior lead-acid battery type resided. And then there are the cylindrical bodied lithium battery cells of varying sizes, from the AA battery to significantly larger cells. And then there is the flat or oblong box shape of lithium battery that is referred to as a prismatic cell or flat cell. Cells, when purchased, need to be matched up correctly so that they will run down together at a concurrent and even rate. This is something when purchasing individual cells that should be clearly stated or requested. Lithium battery cells need to be matched with one another in their internal resistance, so getting matched cells is important. Your average lithium-ion battery cell, be it a cylindrical or prismatic, is usually rated at 3.6 volts, and whatever amp rating you wish to acquire. Sometimes lithium-ion battery cells are advertised as 3.2 or 3.4 volts, but by far and large their rating is more likely to be 3.6 volts, regardless of what it says on their label. There is a special battery electronic resistance gauge tool that can be acquired, but the using of that tool is outside the realm of this tutorial, so you should trust that your battery supplier is pre-testing the cells that they are selling you and making sure if you purchase a batch of, say, 4 cells, all of them have matching resistance and will charge and discharge in sync with one another. You don't want one cell overcharging whilst the others are still trying to catch up. So, matched cells are very important when you come to purchase cells. If you buy an entire battery which has already got cells in it in an enclosure, then you just have to assume, presume, or hope that they are all matched up. And if it's from a decent source, then they will be matched up. It's something that has to be done. A BMS device, I mentioned it earlier. It's usually a small, slender box unit or some electronics that might be adhered to the side of your battery pack or onto the terminals of the batteries. This BMS unit will have wires that run to all the battery cell terminals, and may also have a large high amperage capable relay switch, or even 2. It will monitor the cells, trying to keep them charged up at the same rate and encouraging them to discharge at the same rate. Also, it will stop power being drawn from the battery if it is overheated, and also stop an electric charge being sent to the battery if it is below freezing or freezing. It's a safety mechanism to help maintain the battery at its best performance. There are several different types on the market, several different price points. I'm just going to share with you the meaning of some lithium battery world lingo and terminology. Sometimes you'll see things like 3C, maximum discharge, or 0.5C, maximum charge. The C in this equation, the letter C, it's usually uppercase, but sometimes not, but the C means the amperage rating of your battery or your battery cells. So if you were using, let's say, a 100 amp lithium battery, 3C would mean that that battery might be capable of actually dishing out 3 times the 100 amp rating of the battery over a short period of time. So C is just used to indicate the rating of your battery. Another example, the 0.5C maximum charge indicates that the maximum rate of electric amperage or current that should be sent to this battery in order to charge it up should be no more than 0.5 or half the C, which in this case would be half of 100 or 50 amps. So Clearly, 0.5C in this case would mean that you really shouldn't push any more than 50 amps at the battery when you're trying to charge it up. That's 50 amps would be the max. If you see someone like 4S or 6S or 8S or something S in regards to BMS devices, it's a number then S. The S indicates how many cells you're looking to wire BMS up to. So let's say we were building our own nominal 12 volt 100 amp lithium-ion battery from 4 prismatic cells, that's flat cells, rated at 3.6 volt, 100 amp each. We're going to strap them together to make a block. We connect them together in series using heavy gauge copper jumpers or heavy duty 350 amp grade wire. And we now need a BMS. Well, we would look for a BMS that is rated for 12 volts and 100 amps that could be wired up to monitor 4 battery cells. And that's what the 4S means, or sometimes it's 6S or 8S. It depends on how many cells you're using. You could have a BMS that is designed for 100 amps, but 24 volts, and it was designed to wire up to, let's say, 8 or even 16 batteries. So in short, if you see the number like 4S or 8S or 12S or 16S or even 24S, I mean, I suppose it could even be more, I've not personally come across them, but it doesn't mean they don't exist. Then the S really stands for cell. And I know cell is spelt with the letter C. However, in BMS world, in BMS terminology, they use the letter S to represent cells. So again, it could be 4, 8, 12, 16, sometimes odd numbers as well. I mean, it's a bit weird. And you have to look into if you were looking to buy one, you'd want to match up the number of cells, the total amperage you were looking to work with, and the maximum voltage if you were looking to buy a BMS. One other thing about BMS is there are a number of them out there these days that have Bluetooth connectivity. So you can log into them, into even an interface or, via a phone application or something like that. And you can make changes on the fly to their configuration, establishing, what point they shut off when it gets too cold, at what point they shut off when it gets too hot. The individual batteries, you can monitor them. You can again shut them off when the voltage gets too high or the voltage gets too low, or the combination of the cell stroke batteries inside a larger battery. When any particular one of them again gets too high or too low, then the whole pack shuts off and they go into balancing mode. And what that is really is, like I said earlier, it's very important to try and get lithium-ion battery cells that are balanced when you buy them, in that they all have a similar resistance. However, in the real world, the cells tend to go out of balance a little bit. One will get charged before the others do, or one will discharge faster than the others do. And that being the case, then it's the BMS's job to try and bring them all to the same charge rate and kind of balance them all on the fly. And BMS will do that to an extent. It's easier for the BMS if the batteries are already relatively well balanced. If they're not well balanced, then it becomes quite a lot of work for the BMS, and the whole lot isn't working as efficiently as it might do. But anyway, there you have it, and I hope you have a decent understanding of lithium-ion batteries now.